Hello, folks. In this lecture, we're going to identify the types of chemical compounds, the elements that form them, and how to name some of these compounds. Now, the question that guides us in this lecture is this: is the bonding within all the compounds similar? We begin answering this question looking at the work of the great English scientist Michael Faraday, who in the early 1830s would figure out that some compounds, when thrown into water, would conduct electricity. Now, these compounds would be called either electrolytes, salts, or ionic compounds. They eventually would be found to be compounds in which the atomic particles are held together by electrostatic forces between the oppositely charged particles. Positively charged particles are called cations, and negatively charged particles are anions. Other compounds would not conduct when placed in the water and would be later called molecular compounds or molecules. The atoms in these molecular compounds are held together by the sharing of electrons. As in many things, we find complications in which we have compounds made up of atoms that are held together by both kinds of forces, electrostatic attraction and electron sharing. We will first begin looking at ionic compounds. Once again, ionic compounds are a combination of cations and anions held together by their attractive electrostatic forces. One important thing to remember about ions in chemistry: typical everyday compounds are charge neutral. The compounds are not charged. They don't shock us when we touch them. Thus, the total negative charge of the anions must be equal to the total positive charge of the cations, or we can also say that the system is charge balanced. The periodic table shown here has been seen a couple of times before, but it's critical before looking at ionic compounds in greater detail that we have these monoatomic ions fixed in our minds. Let's first look at some simple type 1 ionic compounds containing monoatomic cations and monoatomic anions. The cations will be metal atoms that have only one possible positive charge. The alkali metals are a good example here. They all have one natural occurring charge in a compound, +1. The classic compound containing an alkali metal is NaCl. The cation, Na+, has a single positive charge balanced by the single negatively charged anion, Cl-. The result is a compound with zero net charge. Now, part of this lesson is also about the nomenclature of the compounds, where the word nomenclature means the systematic method of naming the compounds. So for this type 1 ionic compound, we begin building the name by first writing the name of the cationic metal, which is sodium for NaCl, followed by the base name of the anionic nonmetal, plus the "-ide" suffix. In our NaCl example, the anionic part of the name is chloride. So some of the more typical anion names you need to know are on a table that's shown. So the molecular formula, NaCl, has the name sodium chloride. We need to be able to go the other way as well, where we hear the compound name and then write the molecular formula. For example, let us write down the molecular formula for the type 1 ionic compound magnesium bromide. We know that the first atom is the cation, and we also know, looking at the periodic table in the previous slide, that an alkaline earth metal, such as magnesium in a compound, will have a +2 charge. Bromide is the anion and will always have a -1 charge. So to make a completely charged neutral compound, we need 2 bromide anions for every single magnesium cation. So the molecular formula must be MgBr2. Let's do one more example. What would be the molecular formula for the compound aluminum oxide? From the periodic table with the ions, the aluminum cation is usually a +3 charge, and the oxygen anion will be most of the time a -2 charge. To get the simplest charge-neutral compound, we'll need 2 aluminum cations
giving us a total charge of +6, and 3 oxygen anions, giving us a total charge of -6. Now the compound has a perfect charge balance at this point. So the molecular formula for aluminum oxide must be Al2O3. So what do we do about atoms, which we see on our ionic periodic table, that have varying charge possibilities, like iron ions that can either be Fe2+ or Fe3+? Well, if we have monoatomic ionic compounds, but the atoms can have different charge, we call these type 2 ionic compounds. For example, there are 2 possible iron oxide salts. We know that the oxide anion has a -2 charge. The charge on the oxide is unambiguous. Now the +2 cation of iron will perfectly balance this negative charge, yielding the molecular formula FeO. Notice we don't need to utilize the arrows to get the subscripts, since the cation and the anion are already perfectly balanced in a 1-to-1 ratio. For the +3 cation of iron, the molecular formula, though, will be Fe2O3. The nomenclature will have to distinguish between these 2 different iron-oxygen possibilities. The type 1 naming system is inadequate at this point. There are 2 different ways to name the compounds. One is the IUPAC version of the naming things, which is modern and frankly the easiest way of naming the compounds. The other way to name the compounds is the old familiar names used in the past. Unfortunately, to survive in a lab, you'll need to know both nomenclature conventions. To build the name, we look carefully at the given table of names for the metal cations of various charges. Again, you'll need to be familiar with both the IUPAC and the old names of these cations. Notice that for a given element, the higher charged ion has the old name with an "ic" suffix, and the lower charged ion has the "us" suffix. Take notice, the mercury 1 species is a polyatomic species, Hg2, where we are averaging the +2 charge among each of the 2 mercury atoms, thus assuming each mercury cation has a +1 charge. But when mercury is in this +1 charge, it almost always is in the form of this 2-atom +2 cationic form. To name the compounds, we don't have to change the rules from the previous slide. Using the IUPAC naming convention, the 2 possible oxide salts will be either iron 2 oxide or iron 3 oxide. The old names for these compounds would be ferrous oxide or ferric oxide, respectively. Ions can also be a combination of atoms which, when together, carry an overall charge. These are called polyatomic ions. Now here's a list of them that you need to be familiar with, and it's important to know the formula, charge, and the name. For the polyatomic ions containing oxygen, notice the use of the "ite," "ate" suffixes and the "per," "hypo" prefixes, and their relationship to the number of oxygen atoms within the common elemental series. That should help somewhat in the memorization of these kinds of ions. So, let's use these tables to build the name of a polyatomic ionic compound, COCN2. The parentheses around the CN polyatomic anion makes it clear that we have a +2 cobalt cation because we must charge balance the 2 -1 charged cyanide polyatomic anions. The parentheses are also critical in identifying the polyatomic CN group. COC2N2 may be correct as far as the ratio of the atoms to each other in the compound, and will give us an identical molecular mass as the other molecular formula, but hides the fact that a CO cation is surrounded by 2 cyanide anions. In short, remember to put the parentheses around the polyatomic ions when there is more than one, so the actual structure of the ionic compound is unambiguous. Now, naming is straightforward. We put the cation name first, as we always have, and then the actual name of the polyatomic anion found in the table second. A suffix is not required. So, the name for this compound is cobalt-2 cyanide, or again, we could use the old naming rules and call it cobaltous cyanide.
Well, now that we have a naming convention for the ionic compounds, it's now time to turn our attention to naming all those molecular compounds out there that don't conduct electricity when thrown into water. See you in the next lecture.